Hey, welcome everyone. We've been talking through some FRQs, and this is another one that we're going to be talking through in preparation for the AP Physics C mechanics test. And so we're looking at the 2017. This is FRQ number 3. I got this from the College Board website, so this is all public information that we're working with here. So let's go ahead and take a look at the problem. It has a solid cylinder, rolls down a ramp right here, and then it eventually falls down here, becomes a projectile, launches off, and lands on the floor down below. So this is mostly a conservation of energy, but also a rotation problem as well. And there's more information on the body of the problem right here that I'll let you read right now if you'd like to. All right, so let's go ahead and we're going to just write down one more bit of information on our diagram here, and I'll carry this diagram forward with us throughout the problem. Instead of having all of this, we'll have some room to work with if we kind of summarize the information on this diagram. So they do tell us the rotational inertia is going to be this for the solid cylinder. A synonym for that is the moment of inertia as well. So it's called the moment of inertia or rotational inertia. Either one, same thing. That's our I value right here. All right, so let's take a look at the problems. First of all, for A, it says calculate the total kinetic energy of the cylinder as it reaches the horizontal table. So I've gone ahead and labeled these as 1, 2, and 3. I would do that on my test if I were taking this, just to be clear of what I'm talking about as we go through. It is something you might want to think about doing just so you're clear about what you're doing and what you're working with. So you can think of this as a conservation of energy problem, right, to begin with. And so let's think through this. So first of all, we're going to make a statement something like this. You could call this ME if you want, like mechanical energy, total mechanical energy for the first part is equal to the second part, something like that. If you make a statement like that, a lot of times you can get a point. So that is the foundation for conservation of energy. So we just start with something like that. Then we can write what forms the energy are in. And so the height right here is going to be crucial as this thing starts out at rest. So it does have gravitational potential energy to begin with. And then it has kinetic energy, but we have talked enough about rotation now for you to hopefully be able to understand there are two different types of kinetic energy we need to keep track of. One is going to be the rotational kinetic energy. One is going to be translational kinetic energy. That would be moving from point A to point B. We don't have to keep track of both of those now. It actually turns out that they are asking just for the total kinetic energy. So it actually is even easier than this. We can just start right here with this and say, well, I know this is going to be mgh, where h is just the height of this ramp right here in reference from 1 to 2. So then we say, well, what is that height? Well, that height you can solve for just by doing some simple trig. They make it really easy on you because this is 1 meter and you're working with the sine of 30 degrees, which is half of what it was before. So the height is going to be 0.5. And so you go ahead and you plug in your numbers, and it turns out that you're dealing with 2.45 joules, or 2.5 joules if you use 10 meters a second squared for gravitational acceleration. So that's a really easy intro to the problem, but it is really important to remember. All right, now we have this kinetic energy, the total kinetic energy at the table right here. We have to remember that because most of these problems are going to build on that, right? They're going to expect that you know that information moving forward and you take that and use that information going forward. All right, let's continue. So B says calculate the angular velocity of the cylinder around its axis at the moment it reaches the floor. It's talking about how fast this thing is rotating as it hits the floor. Now I want you to think to yourself, is that going to be the same as it goes through the air? In other words, is this angular velocity right here for 2 going to be the same as at 3? I could ask a couple questions to get you to think about this. Is the rotational kinetic energy going to change while the cylinder is in the air? And the answer is no. It's not going to speed up in terms of its spin or slow down in terms of its spin. What would it need to be able to do that? It would need a torque, right? There's no torque being applied here. And so my second question to get you to think about this, so is the rotational kinetic energy going to be the same at the table and the floor? In other words, is K2 equal to K3? And I hope you can see that the answer is yes. Those kinetic energies are the same. So we can work a conservation of energy problem using 1 to 2 and think about this rotational angular velocity right here, or 2 to 3 and think about this rotational angular velocity here. Either way, it's going to be spinning at the same rates the entire way down because it's just a projectile and there's no torque going on for that. All right, so one thing we can do is we can say, well, I know what this is. I know what my total energy is at point 2. So if we take a look at point 2, we say, well, I know that's going to be my rotational plus my translational for point 2. We had solved for this in A. In fact, I'd put this up here. It's 2.45 joules. So we could say that this is true right here. I'm just plugging in equations that are on my equation sheet. Pretty straightforward so far. The next thing to do is pretty important. So this is in rotational motion. This is translational motion right there. We want to switch from one to the other. In other words, we want to get completely into the rotational side of things in terms of our variables, or completely into the translational side of things with our variables. And there is almost a magical equation that we can use to go about doing that. And that's going to be this. So it's going to be our speed, or tangential speed, sometimes this is called, is equal to our radius times our angular velocity right here. Think about it, this is a translational term and this is a rotational term. What's really important about this equation is it can relate both rotation and translation. And you can select for which one you want to substitute in. It depends on the problem. I've done other problems where I've solved for different ones depending on what the problem needs. And so in this problem, I want you to think to yourself, what do we need? What is the problem asking of us? The problem is asking of us angular velocity. We want to change this right here into the rotational form. So I'm going to go ahead and take this v value and sub in r omega, and that's what I have down here. Just a couple other things going on. I do know what the moment of inertia is, or the rotational inertia is. So I'm going to go ahead and take that and sub that in right here, and I'm going to label this equation as 1 so that when I move to the next slide you'll know what I'm talking about. And so we're going to continue simplifying the problem here. So we're just doing some algebra here. We want to simplify the problem, we want to get common denominators and simplify as we can. And this is what we have right here. We will break this down even more, so let's continue. We can go ahead and plug in some numbers here. I'm going to label this as equation 2 as I go to the next slide so you can see what I'm talking about. We continue to plug in our numbers and we can solve for omega. We can solve for the angular velocity, which is what they're asking of us. It turns out that's going to be 25.6 radians per second. So that's how fast this thing is spinning here and all throughout the air, and as it hits the ground. It doesn't get faster as it goes through the air. In terms of its spin, it doesn't slow down. It's just the same spin as it goes through the air. So at point 2 and at point 3, we know what the angular velocity is going to be. C says calculate the ratio of the rotational kinetic energy to the total kinetic energy for the cylinder at the moment it reaches the floor. Alright, so let's go ahead and work through the problem as we would normally work through this problem, as it kind of makes sense. Because if you look at this, you're looking at 2 to 3 now. It's talking about as the moment it reaches the floor. It may be very tempting to think of this just as a normal conservation of energy problem, and that's typically how you would approach the problem and begin the problem. And so let's go ahead and think what will happen if we do that. First of all, let's talk about what we mean by a ratio. This is really crucial and foundational and something they're expected to do and know, but I think sometimes students forget this, and so I want to quickly go over this. If you're asked for the ratio of just anything, A to B we'll call it, another way of writing that would be A colon B, and then you could just do a fraction of A over B. That's literally what we're talking about when we do a ratio. So if you have forgotten that, and you're embarrassed to admit that, just keep that in the back of your mind. Oh yeah, if we're comparing A to B, then it's just A over B, so to speak. Alright, so let's continue. If we start thinking about this as a conservation of energy problem, this is how, at first glance, we might start thinking about this. What you would do is start talking about your energies, and it starts to get more complex, right? So we had avoided doing this previously, working from 2 to 3. Instead, we worked from 1 to 2. If you're working from 2 to 3, things start to get more complex because we don't know some of these answers. We don't know what our translational motion is, for instance. But we do know, for instance here, we do know that these rotational values are going to be the same, and if they're the same, we can cancel them out. So I can cancel this out, as well as this out, and that's what I'm showing right here. But it does turn out that this isn't all that helpful. This is going to take us down a rabbit hole that'll take us longer. We do learn something useful though. The difference in the translational kinetic energy between 2 and 3 points, what I'm calling points 2 and 3, is the height value. So that height energy added to the kinetic energy at 2 for translational situation is equal to the translational kinetic energy at 3. And so that's useful information. So it is useful information, but we're starting to get to the point where the time devoted to the strategy is not paying off for us. So sometimes when I get to a problem, and I think when you get to a problem, a useful thing is if you're trying to work your way forwards and you're kind of hitting a brick wall or it's taking way too long, sometimes it's useful to work backwards. So let's go ahead and rethink this problem. Instead of a standard conservation of energy, let's work backwards from what the question is asking of us. Remember, it's asking for A to B. It's asking for the ratio of the rotational kinetic energy to the total kinetic energy for the cylinder at the moment it reaches the floor. So let's go ahead and think through how we could talk about this. If we just set this up, it's asking us for this, and we say, all right, well, I know this portion and these portions down here. I did learn something really useful with my work in the last slide, and that is I did have a certain amount of translational kinetic energy here. I do need to add in the height value because that changes this. So that would be these two terms right here would be the equivalent to the translational kinetic energy for point 3. I proved that on the last page, and so that actually was helpful. And it may have been kind of a dead end, but it did help us to clarify what we're talking about. So let's continue with this. We can go ahead and plug in some equations here. I'm going to label this as 3 because I'm running out of room. We did do some previous work over here. We did solve for this business. And so I'm going to show you what I mean by that. Let's continue to the next slide. That is our work that we have done so far. At this point, you can find two different things. So depending on what you spot in your previous work, you could say, well, look, I know what this is in terms of a number. I know it's 2.45 joules. You could do the problem that way. Or you could say, well, look, I did in my previous work, I'd solve for this. And I know what that is. So this is the energy, the total kinetic energy at point 2 essentially here. And so I solved for this already. I could sub that in. So either way you do the problem, I'm going to continue with the left-hand side because there's more algebra to show than with the right-hand side. So if we continue with the left-hand side, we end up with something like this. Now we're going to want to start thinking about like terms and simplifying. I'm going to label this as equation 4 as we continue to the next slide. So this is what we have so far, and we can cancel out our masses and plug in our numbers, and it turns out that we end up with a ratio of 0.133. This is a unitless answer because whatever units we have up top should cancel out the units down below, and that's what we have. And so yeah, that's our answer for C. And so to summarize what we have gone over with C, remember a lot of times it makes sense to work the problem forwards, but occasionally it actually is easier if you work the problem backwards. So occasionally you work a problem, you're like, this is going to take too long. I can't spend 10 minutes on this one section of this problem. If you hit a roadblock like that, you might want to start the problem and work backwards and see where you can meet in the middle. And that's what we did here. All right, let's talk about D. So it says calculate the horizontal distance D. Well, as it goes from 2 to 3, essentially it's just a projectile. And hopefully this will be easy points for you that you can do relatively quickly. So if you go ahead and you start with this equation, which is on your equation sheet, we think to yourself, all right, this is not launched up or down. It's a horizontally launched projectile. So that initial velocity in the y-axis is 0. That means that term drops out. These two things consolidate into a delta y. I can continue with this and plug in some numbers. I end up with the time that it takes for this thing to hit the floor. That's going to be really useful as we continue the problem. It's just a simple projectile problem. When we work this in the x, remember there's no acceleration in the x here. We're not dealing with drag forces in this problem or anything like that. And so as a result, you can do this. And here at this point, we are going to sub in. We don't know what our initial velocity is right here at 2, but remember we can use this sort of magical equation here as we relate rotational and translational motion. And so we're going to say we don't know what this is, but let's put this in terms of rotational variables, which we do know. Therefore, we would end up with this. Delta x is equal to r omega time. And we can go ahead and plug in our numbers. It turns out that d is going to be equal to 1 meter. Okay, and so for the remainder of the problem, it's now talking about a sphere, and we're going to do comparisons between the sphere and our cylinder that we were working with previously. It says a sphere, the same mass and radius, is now rolled down an inclined plane. The rotational inertia of a sphere around its center is given over here. Is the total kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the total kinetic energy of the cylinder at the moment it reaches the floor? Okay, and so this one is pretty easy. Hopefully you can see this. Think about it for a moment. What you're going to say is they are going to be equal to each other. So the reason for that is they both start for the same height. They both have the same mass. Yes, they have different moments of inertia, but essentially the amount of energy that they have to deal with is dependent on the height and the mass and gravitational acceleration. And so those things are the same, which means this kinetic energy is going to be the same for both the sphere and the cylinder. All right, let's take a look at E2 or EII. It says, is the rotational kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the rotational kinetic energy of the cylinder at the moment it reaches the floor? Okay, so it's important to note that we're talking just about the rotational kinetic energy, not the kinetic energy in total, the rotational kinetic energy. So now we have to backwards sort of think to ourselves, all right, well, which one is going to be moving faster, and so on. So it turns out that if you look at this, this has 1/2 mr squared, so that's going to be a 0.5 coefficient out in front. This is a 0.4 coefficient out in front right here. This has less, the sphere has less of a moment of inertia. What that means is it's easier for the sphere to turn, and so it actually will move quickly as it goes down the ramp. So that means this will move faster as it goes down the ramp. And because the sphere is moving faster as it goes down the ramp, it has a greater linear speed, and they both start with the same energy. And so if we're saying that more of the energy, more of that same energy, think about like each of these things have 100 joules of energy, let's say. Just make it easy and say, well, out of that 100 joules of total energy I have, I'm going to spend a greater amount on the translational speed. And if that's true, then I have less on the rotational side of things, right? Like you only have a certain amount of energy. If it's moving translationally from point A to point B faster, the sphere is moving faster in that regard, then that means it must have less rotational energy. And that's how we reason through and get less than. Think about this. You may need to listen to this explanation and read this explanation more than once, because if you've never heard this before, this is worth slowing down and thinking through the answer for. All right, in E3, is the horizontal distance the sphere travels from the table to where it hits the floor greater than, less than, or equal to the horizontal distance the cylinder travels from the table to where it hits the floor? So think about it. If the sphere is moving faster than the cylinder, the sphere is going to go out farther and have a greater d value than the cylinder will, which will just fall down and not have as great of a d value because they'll both hit the ground with the same amount of time, but if the sphere has a greater initial velocity, it's going to shoot out farther. So that's how you justify E3, and you would write something about that. Hopefully this has been helpful. I'm going to be doing other screencasts as well to get everyone ready for this AP Physics C mechanics test. So if you'd like to listen to some more, please do so. Thank you for listening. Have a great day.